Okay, so I would like to introduce you to our first lecture for today, officially, and it's called Memory Corruption, Why We Can't Have Nice Things by Gannimo. Enjoy.
Hi guys, it's a pleasure to be here. I'm Matthias Peyer, or Gannimo. I'm a research faculty at Purdue University, and I lead the HexHive research group, where we collaboratively try to solve different hard challenges in software security. And we try to develop new defense mechanisms for different forms of software-based attacks, hacks, and so on, but also try to develop new attack vectors. And today, I will talk to you about memory corruption, which is a research focus in our group. And we'll see why we can't have nice things. So overall, the story that I'm going to tell you is how I learned to stop worrying and embrace the seg fault over the course of several years. So in the end, we are facing a problem that software is unsafe and insecure. We have millions upon millions of lines of code written in C and C++, and these languages trade type safety and memory safety for some potential or promise of performance. And if you're programming in these languages, the programmer is fully responsible for all the checks, for all the security checks, bounds checks, memory safety checks, type safety checks, and so on. And as we know, programmers are very likely to screw up, especially if the language makes it very easy for you to screw up. And there's a tremendous amount of software out there that is written in these languages. Think about the base system that you're running, the operating system kernel, the hypervisor, and most of the applications that you have on your system. They're all written in C and C++. And even when new applications are being developed, they are started in C++ because of the promise of performance. Think of the Google Chrome browser, which is an insanely big C++ project with about, I think, 15 or 20 million lines of code, which is all written in C++. And although Google has very strict coding standards, Chrome is being pwned year after year, again and again, and we are finding a large amount of vulnerabilities in there. And there are just way too many bugs out there in the software to find and fix them all manually. So what we are doing in our research group is to protect the integrity or find mechanisms that protect the integrity of software mechanisms through some forms of safe runtime systems. So we're trying to make systems resilient against underlying attacks. So even if you do have a memory corruption vulnerability in your system, we will detect this corruption when it is being exploited and then terminate the system, protecting the integrity of the whole system and your data at a slight performance cost. So a couple of years ago, we looked at Heartbleed. And who of you guys has heard of Heartbleed? Just a quick show of hands. So most of you have. Who has not heard of Heartbleed? Okay, so about half of you have heard of Heartbleed. About a tenth have not heard about Heartbleed. The others have no opinion. So Heartbleed was, or is, this very nice memory or information, this very nice information leak that was present in an open SSL library. So you are sending the server a request, hey, please reply to me an echo packet, and I want you to reply the string hi with 2 letters. And the server parsed the message and said, oh, I've got a request incoming, I should reply hi in 2 letters, and it was sending 2 letters back. But an evil attacker could craft the message, hey server, please echo to me hi with 200 characters. And then the server happily copied whatever was behind this string, where it was allocated in memory, and disclosed different forms of, or different pieces of memory, which allowed the attacker to read passwords, SSL keys, and so on from the memory of the system. So we worked on, or when we heard about this attack, we thought, hey, this is a very severe attack. We have to measure if people are actually able to patch the systems after they learn about it and how they patch it. And what we did is we did internet-wide scans 2 days after the vulnerability was disclosed, and we scanned every single system out there and checked if the vulnerability was still present. Most of the credit for this work goes to the folks at UIUC, University of Michigan, UC Berkeley, ICSI, and I was just a small component in there that helped look at the results a little bit. So we did these scans, and we had to develop a mechanism to figure out if a system was vulnerable or not. And as this was a university project, we had lawyers breathing down our necks so that we had to make really, really sure that we were not exploiting the vulnerability. Because how would you explain to a lawyer that you just exploited all the systems on the internet? This would lead to a very, very bad press. So we developed a mechanism that allowed us to test for the vulnerability without exploiting it. So we connected over SSL, and the vulnerable SSL version had an additional software bug. So if you replied, or if you asked the server, please send me an echo package with 0 bytes, the protocol should return an error, but the vulnerable version returned a packet of length 0. So we were not reading any bytes of the memory of the server. We were perfectly fine, and we had a way to test for the vulnerability. So we tested all the servers out there, and we started 2 days after disclosure of the attack, and we found that a huge amount of the systems were still vulnerable. And we looked at the full IPv4 address range, and also at the top 1 million domains. And patching happened very, very slowly. So people or attackers had a large amount of time to actually prepare their attacks and read out all private keys. So you had to consider that all private keys were disclosed and vulnerable. Interestingly, 11% of servers remained vulnerable even after 48 hours after the public disclosure of the attack, which is a very long time, especially if you consider that your user base is completely vulnerable and everybody can snoop in on your connections after that. Patching plateaued at 4%. So at one point in time, a large amount of system administrators didn't even care about patching. So they just kept the vulnerable versions running. Interestingly, what we also found out, only 10% of the vulnerable sites actually replaced their certificates. And after your private keys leaked, you should totally replace your certificate, because otherwise it's not really useful to, even if you've updated the server, because people can still read out your connections. And even worse, of the people that actually replaced their certificates, 15% of those replaced the certificates with vulnerable cryptographic keys. So they reduced the amount of security even more. So this is a terrible, terrible process. So what we can conclude is that the update process is slow, incomplete, and often incorrect. And it's just terrible out there. And over the last couple of years, we had a large amount of security outbreaks, which was awesome for me because I was applying for a lot of funding. So I had a lot of good examples to give to the funding agency. So there was Heartbleed out there was Shell Shock, and Ghost. So these were all very nice vulnerability that allowed me to acquire more funding in the area of memory safety or memory unsafety. So let's just look a little bit at different problems that we are facing in memory safety. And we'll talk about 2 different aspects of memory safety and then how this leads to possible exploits. So at the core, memory safety, if you're programming in C, or who of you are C programmers? Who has written more than 1,000 lines of C? 10,000? 100,000? Who has written an operating system? Okay, a bunch. So you guys are well aware of the different kinds of vulnerabilities in there. But let me just repeat for those that are not as proficient in C. So there's 2 kinds of invalid dereferences that can happen when you're programming in C. There's a dangling pointer. So this is a temporal memory safety violation, as we call it. And at one point in time, the pointer that you have, the reference, points to a valid object. But later on, you free that object, you return it back to memory, or you return from the function call that allocated the object on the stack. So it is no longer valid. But the pointer still points to that object that was now dereferenced, that was now deallocated. And maybe something else is allocated on its behalf. So after it is freed, if you use it, it results in an invalid dereference and a memory safety violation. The second form of memory safety violation is an out-of-bound pointer, we call this a spatial memory error. So at one point in time, the pointer was pointing at a valid memory location, and as we keep computing, we might be iterating the pointer. Maybe we are walking through an array and accessing individual elements of an array. And later, at a later point in time, the pointer points outside of the bounds of the underlying object that it was allocated to. So we allocate an object and we access it out of bounds. So according to the C language standard, it's perfectly fine to have pointers pointing to invalid locations. So you're free to have as many of these pointers as you want. The only bad stuff happens as soon if the pointer is read, written, or freed again. So if you do an action on this invalid pointer, and then bad things happen. And according to the C language standard, this is undefined behavior, and this is where all the attacks live. They all live in this undefined behavior space. So these are the two main forms of memory unsafety that we had in the past. In recent years, another problem became more and more prominent, especially when exploiting large software systems like Google Chrome or GTK or different other forms of C++ programs. The JVM is another nice example for that. And that's the so-called type confusion attack. So if you're programming in C++, you are allocating classes. And we have a very simple class P here that has a data field. And we extend this class as called class C, and we add a second form of data. So you do have memory objects with two pieces of data, two slots, the P data and the C data. Now, if we allocate a new P, so we allocate it somewhere on a heap, we allocate a memory object that has the size of P data. And in C++, for performance reasons, you can do a static cast that casts an object from one type, for example, P, into another type, for example, C. So the object at location C, or the C pointer, now assumes that you have the total size of a C object. But before, we only allocated an object for P. And this works well as long as you only use the fields that were present in P. But as soon as you access the C data field, you have a memory corruption. And the type confusion actually happens at the time of the static cast, because the downcast is not legal from the type to the parent type. And then we have a second memory safety violation, which would be an out-of-bounds violation here, as soon as we access that data. But interestingly, the initial violation happens at the time of the static cast. So building on these types of memory safety violations, either the spatial, temporal types of memory safety violations or the type confusion, we can form two types of attacks. There are the fun control flow hijack attacks, which allow the attacker to execute different forms of code, or there are data-only attacks which allow the attacker to leak some pieces of memory. And for example, the Heartbleed bug was an information leak that allowed the attacker to leak information. But let's focus on the fun code execution part first. Or let's focus here on the code execution part. So a control flow hijack attack is if we are executing new code that was not intended by the program. Think of the program as an abstract graph that connects individual pieces. So you can project or you can transform the program that you're executing into some form of execution graph that executes one step after the other. And the individual basic blocks can be pieces or nodes in the graph, and the edges are connections between these basic blocks. So here, for example, we would have some form of if condition or a loop from as long as the loop condition in basic block 1 is true, we execute basic block and return to block 1. So this is the representation of a loop. As soon as the loop condition is false, we go to basic block number 3 and execute the statements after the loop, and then continue to basic block 4. Now, in a benign execution, the execution will always stay inside this existing graph, and we can abstract this graph somehow. In an attack form, at one point in time, the attacker is able to overwrite a code pointer. And the attacker modifies the code pointer, and this could be either the return address on the stack that encodes where you were coming from so that you can transform control to an alternate location. It could be a function pointer in C that's somewhere on the heap or on the stack, or it could be the vtable pointer in C++. So for C++, to allow dynamic dispatch, we have some form of vtable pointer with a set of code pointers that an attacker can then modify to redirect somewhere else. So assuming the attacker has modified any of these 3 types of code pointers, the control flow at one point in time leaves this predefined graph, leaves this valid graph, and we now have a control flow hijack attack, and we can reuse existing code to level for a first stage attack, and for example do a return-oriented programming attack, jump-oriented programming attack, to then inject more code for to execute in a third stage. So this sounds very, very theoretical. So let's make a more practical example. We have a small snippet of C code here, and I'll give you 2 seconds to think about the vulnerability. So we assume that the attacker can control both arguments to the function. We do have a function pointer in the function, and then we calculate an offset of the buffer and then use this later on. So if you look at memory, the memory looks somewhat like this. We do have storage space for Q, for buffer, for a function pointer, and some code. And Q is actually supposed to point somewhere into buffer. So the goal of the function was the programmer intended Q to point into the buffer so that the user could modify a value in that buffer. Think of it as an array where you're changing some value somewhere in between. Now, at this point in time, the attacker, the attacker controls the offset as a first parameter, the attacker can actually modify Q and implement it in a way so that Q points to the function pointer, to the precise location of the function pointer. And this works if we know the distance between the buffer object and the function pointer on the stack or on the heap. So now Q points to the function pointer. And interestingly, so the benign code sets the function pointer to point to the value of foo. So as execution continues, function pointer is set to the value of foo. But at a later point in time, when the value in the buffer is actually set to the user-defined value, as Q is now pointing to the function pointer, the attacker is able to overwrite this function pointer and modify it. So the attacker can point the function pointer somewhere else. And in most cases, this will lead to some form of segmentation fault because you're jumping somewhere into the weeds. But if you align it correctly, if the attacker knows where individual code snippets are, the attacker can redirect it to the first form of gadget, to the first execution gadget, and then execute arbitrary code. And this gets the attacker full control of the system, and most times the attackers will then make another piece of code executable that gives them more functionalities and more permissions. So this is some form of privilege escalation attack where the attacker can then gain control. So we've now gained control of the system. There are a whole bunch of defense systems. Over the last 30 years, we've developed a plethora of defense mechanisms. And some of them actually made it into real systems. So we do have many different defense mechanisms out there. And let's just look at the ones that are available on your everyday computer or on your smartphone or in your tablet. If you have a view of memory, back in the old days, everything was at fixed addresses. So the stack was always at the same address, the data section was always at the same address, and the text section was at the same address as well. So everything was well known to the attacker, and the attacker could abuse all these features. Also, the old systems did not distinguish between executable code and data, so you could just jump to any data and execute this as code. And many times the code section were writable as well, especially on microcontrollers. This is still true because you don't have these permission bits. But on desktop systems and smartphones, we've developed a large amount of defenses building on that. So there's data execution prevention, which removes the executable bit of any page that is mapped as data, so that nowadays on a heap and on a stack, you can no longer have code. You can only have code in code regions. And all the code regions must be mapped as read-only, so you cannot execute these regions. So this makes it harder for the attacker to inject code. But clever attackers actually reuse code in different ways and stitch together pieces and snippets of the existing code region to circumvent this protection. Therefore, there's address-based layout randomization. So instead of using well-known locations, we just shuffle all these regions around so that the attacker does not know where the individual pieces of code are. And this helps us in hiding information from the attacker. So the attacker first needs some auxiliary attack to learn all the locations of the code. So that makes it harder. If the attacker does not know where the code snippets are, the attacker cannot reuse it. Simple case. In addition to that, we have stack canaries that are a simple defense against stack-based buffer overflows, and safe exception handlers that help against some form of overflows as well. Think of those canaries as some form of special values that are injected somewhere in the stack, and you can continue to check these values if you still have the correct value. If the attacker overwrote those values, you know that something has gone wrong, and you can terminate the application. So if you look at the status of the deployed defenses, we know that ASLR and data execution prevention are only effective in combination. Only if you have both defenses running at the same time, you can stop an attack. If an attacker learns the pieces or the locations of code, you can get around both of the defenses one after the other. And as soon as you break ASLR, you get code reuse, and then you can build up your second stage of the attack. And on desktops, information leaks are fairly common, especially on the Windows system, so they make it easy for you to detect these attacks. On servers, code reuse attacks have decreased because it's gotten much harder to leak this underlying information. So interestingly, we had an attack at Wood last year, and some colleagues had a follow-up paper at Oakland this year, which are two security conferences, that show that you can leak the base addresses of ASLR with very high probability. And this is a very, very fun attack because you break ASLR, you can reuse code, and then you can go and rob yourself away and start owning the machine. So if you look at what's actually deployed on the system, and we look what kind of attacks are happening, we are way past that. So the defenses are completely failing us and stopping us, and we are stumbling along the way, and it's just breaking all over the place. And we're doing a terrible job at securing our systems. So what we need are more principled defenses that have type safety, stack integrity, and control flow integrity. So I'm trying to show you here some interesting mechanisms that we are developing in academia and trying to push through onto real system so that we can have principled defenses against attacks. And I'll start with a sneak preview of a paper we got accepted at CCS this year, which is one of the top security conferences. So we'll present this in a couple of weeks in Vienna. And this is with a couple of colleagues of mine from Freie University and a couple of my students at Purdue University, where we enforce strong type safety for applications written in C++. So again, we have the two objects, and we use the same code as in the type safety example as before. We have the object P, and we have the object C that extends object P. Now we're allocating object P, as we did before, but in addition to that, we have a so-called metadata table that stores for each object, for each address of the object, what kind of type it is. So we remember the type and the type hierarchy of the object. So as soon as we see cast, we can look up the underlying type of it. So we wrote a compiler pass, and we implemented this on top of LLVM, and this is open sourced, that replaces every single static cast that is in the source code with our own function that does a check cast. So we make all the casts explicit, which leads to a slight overhead of a couple of %, but we are checking every single typecast at runtime. So at the point of this cast, and not at the later stage when the data is used, we detect there's a type confusion, and we can terminate the program and give the programmer some feedback. Hey, a type confusion happened. I expected an object of type C, but the underlying object was actually of type P. So these types cannot be cast into each other, and we can thereby terminate the application and tell the programmer, hey, you need to fix this. And this is a principled defense that we will detect all these type confusion problems and stop the underlying exploitation as it continues. And if you look back at the last couple of vulnerabilities against the Chrome browser, these were all type confusion vulnerabilities. Another principled defense that we looked at is stack integrity. So enforcing dynamic restrictions on return instructions. So if you have function returns, return pointer on the stack is basically a pointer, code pointer that can reach arbitrary code. So we protect the return instruction through some form of shadow stack or safe stack that ensures full integrity for these instructions. So if you have these two functions, A and B, they both call foo, and you have a function foo. If you have the control flow graph, if we know that you're calling foo from function A, we will remember that the origin came from function A. So when we are returning from foo, the only location that you can reach or that you're allowed to reach is function A. And we do this check at the return instruction point. On the other hand, if you're calling from function B, we make sure that the only place that you can reach when you're returning is function B. So we ensure the integrity of the code pointer on the stack. So the attacker is unable to modify this code pointer, or modifications will be detected and we terminate the application. So this is a strong property that guarantees that the attacker cannot use return-oriented programming, because we will detect it in any case. Another hot topic is control flow integrity. Let me do a quick poll. Who of you has heard of control flow integrity? About 5. Did anybody hear about control flow guard? The new defense mechanism that Microsoft added to the recent Visual Studio. So there was one, I think, 1 or 2. So control flow integrity is a defense mechanism that restricts the allowed targets that an indirect control flow transfer is allowed to reach. So if you have a function pointer, in principle, this function pointer can reach any executable address in memory of the program. And so you have a sheer unlimited amount of possible targets. And on x86, every addressable location in memory does not mean every single instruction, but you can jump inside instructions as well for extra fun. So what control flow integrity does, it uses an analysis to figure out the valid targets. So it executes an additional check before the function pointer is used. And using this analysis that is usually done statically before the execution of the program, you figure out which of the targets are actually allowed. So at runtime you check, is it one of these 2 targets that we allowed? If not, if it is any other target, or if the attacker was able to change it using some form of memory corruption, we stop the execution of the program right there. So we are limiting the amount of targets. And this can happen on the heap when using a function pointer or a virtual call in C++, but also on the stack. We check the return target and check if the target is in one of the sets, one of the allowed callers. So if it is one of the allowed callers, we allow the return target. Now, when looking at the stack, this is slightly different than the property that we defined for stack integrity. because we have a set of allowed targets. Now let's look at the example again. So the attacker may write to memory. The code pointers are only verified when they are used later on. So when we are looking again at the same example, and we have the two possible calls from A or B to function foo, the analysis will go through the source code and detect, hey, there's one possible call to foo from function A. So function A may call function foo. But the analysis found that both A and B may call function foo. So at the return point, when function foo returns, both targets, either A and B, are valid, because they are both in the statically known set of possible call locations. So the attacker can construct the same analysis and figure out what the possible call targets are. So instead of being able to return to any possible location, as we usually do in return-oriented programming, we now have a set of locations that are allowed. In practice, there would only be one valid location, but CFI restricts it to a smaller set of locations that are all possibly valid. And the attacker is able to exploit this and select any of these possible locations at his or her choosing. So did you take your notes? The attacker may be able to exploit this by changing and shifting between these things. And there are a couple of novel code reuse attacks that we can develop this way. And last year we developed control flow bending, and there have been a couple of additional attacks building on top of that that were published more recently. So we construct the same analysis that the CFI mechanism does, and we construct a control flow graph. So we define the valid graph of control flow that the attacker or the program is allowed to follow. And we then steer the execution of the program along those graphs. So we know that CFI is stateless. So for each of the possible locations, we can redirect it according to our choosing and thereby achieve reasonable side effects. So according to our control flow bending technique, we make sure that every single control flow transfer that is executed is valid according to the security policy. But if you would observe the execution trace, it would not be a valid execution of the program. And this allows us to circumvent static, fully precise CFI and get around this defense mechanism. The underlying limitation of CFI is that it's stateless. So each state is verified without context. So if you would validate the complete path of the program, you could make sure that the attacker cannot redirect it, because the path dependencies will make sure that only one possible target is valid. So we keep bending the control flow along valid paths that are undetectable. And we search a path in this control flow graph that matches the desired behavior of the attacker. And the desired behavior is usually executing code, reaching system, and then supplying the argument so that we can escalate our privileges. Other academics have already shown that weak control flow integrity that uses a weak analysis is already broken. So we are not looking into that much further. And Microsoft's control flow guard is an instance of a weak CFI mechanism. So it makes exploitation a little harder, but it can be mitigated in pretty much all cases. And the attacker is able, if you devise a clever attack, to get around it. Microsoft consciously chooses to make a weak implementation because it's a trade-off between usability and the complexity of the software. So they traded off security for ease of deployability. Let's look at strong CFI and what we can do if we would have a strong CFI. So we assume that the underlying CFI defense mechanism uses a strong control flow graph without any over-approximation. We assume stack integrity through, for example, a shadow stack, and then assume that a control flow transfer is only valid if some benign execution actually executes it. So how secure is it? And we evaluate two different options, with and without stack integrity. So without stack integrity, we obviously want to do ROP. So we have to find a path to system in our control flow graph. So we look at the graph of the execution, how the different program nodes are connected, and we try to divert, as part of our attack, the control flow of the application to reach this point in time. So we are constrained through the memory vulnerability, and we set individual memory location so that the program follows this path and then reaches system with arguments that we control. So how does the control flow graph actually look like? People thought for a very long time that these control flow graphs are very, very complex. So it would be almost impossible to find a path from the location where we control the arguments at the vulnerability for the vulnerable function to the actual system call that we want to reach. So it is immensely complex to control all the arguments along this path. And the attack would be highly unlikely. And people thought that this makes the system very secure. What we found out that a control flow graph actually looks like this. There are a lot of functions in there that are pretty much connected everywhere. Think about memcopy. Think about printf. Those functions are called from so many contexts. And remember, if you're returning from this function, you can pretty much return to any location that calls this function. And this allows us to connect different parts of the complex control flow graph in a very, very easy manner. And for example, for memcopy, this is what we call a powerful dispatcher function, and allows us to redirect the call easily and then control the arguments to system. Now, dispatcher functions are frequently called, and the arguments are under the attacker's control, and they may override their own return address. And we found a whole bunch of examples of these dispatcher functions that are pretty much everywhere in the code, which makes exploitation on the stack very easy. So if you do have a memcopy, we have a caller stack frame, we have the stack frame of memcopy, and the stack frame of the memcopy function is divided into the return address and local data. If we adjust the locations correctly, we can overwrite the call to memcopy so that the attacker or the attacker's return address is written into the return address of the function, and then return to any of the possible callers. And this allows us to connect pretty much arbitrary graphs on the control flow graph from one node to the other. And we can jump around in the control flow graph and get from one end of the program to the other end to then reach system as we want. If we do have stack integrity, so we know CFI without stack integrity is broken, like broken beyond repair. And stateless defenses are insufficient for stack attacks. So we need to have some form of stack integrity. That's why we pushed the stack integrity approach that we did 2 years ago into LLVM. And if you use LLVM with the argument to use safe stack with stack integrity, you're using our mechanism to protect your stack against such forms of attacks. So this is actually out in regular LLVMs. If you're compiling your software, use the safe stack to make your systems more secure. If we do have stack integrity, the attack becomes program dependent. And we found that in many cases, we are protected against attacks. So just to remember for control flow integrity, if you do have indirect control flow transfers, like indirect jumps, indirect calls or so, the individual targets are encoded in these equivalence classes. So there are multiple targets that are allowed for each target. And this is what we are exploiting in this attack. And the size of the class is crucial for the effectiveness of control flow integrity. And we actually evaluated about 50 or 60 approaches that were proposed and looked at how precise they were in their underlying analysis. And we compared all of them and tried to exploit them. And just to show you a couple, there's the Google IFCC, which is in LLVM as well, the Microsoft Control Flow Guard, LLVM Control Flow Integrity, and MCFI, PyCFI, and a binary-only approach called Lockdown. And we tested all of them for control flow bending. The forward edge specifies the protection for indirect calls and indirect jumps. The backward edge protects the return targets. And you see that the first 3 of them the Google IFCC, Microsoft Control Flow Guard, and LLVM CFI don't protect the backward edge at all. So we can easily do control flow bending for all of them. Out of those three, the first two we found are very imprecise. They have very large equivalence classes and easily allow attacks on the forward edge as well. LLVM CFI is rather precise and protects the forward edge. So as soon as they protect the backward edge with a shadow stack or a safe stack, LLVM CFI will be very effective. MCFI is rather effective on the forward edge and somewhat effective on the backward edge. And Lockdown uses a shadow stack, but due to the binary-only approach, it is only reasonably effective on the forward edge. So what if we have stack integrity? Many times, ROP is no longer an option. The attack becomes much harder. So we need to find a path through the program that uses different forms of virtual calls. And if you guys are interested in that, look up the COAP counterfeit object-oriented programming attack that simplifies and describes this process. And in the end, if we would have a subset of the program that allows us to inject code and execute code, this would make the attacks much simpler. And if we can automate this, this would be very awesome, and we can just go and start execute stuff. So what we introduce is printf-oriented programming. Assume that you can execute or you get control of a format string. And we've shown that format strings are Turing complete. Do you guys know what Turing completeness is? Who knows what Turing completeness is? Okay, half of you. Turing completeness defines that you can compute an arbitrary function. So if an interpreter is Turing complete, you can use it to compute arbitrary functionality. So you can pretty much execute any arbitrary code. It's mostly an academic exercise that hackers don't really care about. But for us academics, it is a nice proof and simple proof of concept. And we showed that printf is Turing complete. So you can do memory reads, you can do memory writes, and you can do conditional instructions. And loops are implemented in a way that if you have two calls to the same function, if you have no stack integrity, you can return to the first loop and thereby implement the loop and you get your Turing completeness. So the program counter becomes the format string counter and you can use that to execute arbitrary code. So this is very complex to construct. And Nicholas Carlini at UC Berkeley did this awesome implementation of a full interpreter that we developed as a domain-specific language. So you can use an arbitrary programming language, and you can write your program in a string, and then if you control the arguments to any printf, you can execute arbitrary behavior. Have you ever heard of brainfuck? Who's known brainfuck so far? Okay, most of you. Brainfuck is an awesome little language that is Turing complete, allows you to do arbitrary computations, and so it only consists of these 8 instructions on a side. So you can go forward with the data pointer, you can go backward with the data pointer, you can increment the data pointer, you can decrement the data pointer. There's an if, a put char, and a get char. So you can read input and output, and this allows you to do arbitrary computation. Now, we went through the process and defined format strings for each of those instructions. So you can have a format string for each of these little things, and if you connect them in a specific way, you can then execute an arbitrary brainfuck program. So assume that you have a program that calls printf in a loop. We divide the execution of the brainfuck program into 4 stages. If you ever had a computer architecture class, an instruction is executed on your system by first decoding the instruction, executing the instruction, updating the program counter, and then possibly writing back to memory. And we followed the same approach. So we have 4 calls to printf. So if you're calling printf in a loop, you're iterating through these 4 calls. You are fetching the instruction, executing it, updating the PC, and then you're printing it. So you can now pass a format string that contains a brainfuck program into an exploit that overrides the format string for printf and execute arbitrary computations. How awesome is that? So let's do a very quick demo and look at how that happens, if I'm able to bring the screen over there. Okay, so I got my files here. I'll make it clean. I do have the example here. And we'll just scroll down. This is pretty much the example that I showed you before on this slide. So we do have the loop here that executes one brainfuck instruction and the interpreter loop. So we just assume that this is the main function where we inject some code into. So this is just a simple program that allows us to inject code and override the individual format strings. And we have the execution of the instruction and the update of the PC. So all this code is on GitHub, so you can check it out and test it yourself and make sure that I'm not cheating. And using my awesome Python skills, I wrote a small program that translates an arbitrary brainfuck program into a format string that is then injected into the program and passed as arguments so that we can then inject the program and execute it as part of the format string. So imagine that the target program does, in a loop, a call to printf. And we are hijacking that call to printf to inject an arbitrary brainfuck program. And I've got a couple of brainfuck programs here. Let's see This is Hello World in brainfuck. So we are iterating through the different cells. Huh?
40 lines.
Yes. Well, this is commented, so it added a little bit. And we also have a Sierpinski triangle, a brainfuck program that prints a Sierpinski triangle formatted as a Sierpinski triangle. Brainfuck is an awesome language. So let's translate these two programs, brainfuck programs, into format strings that we can inject into our small little program. And I've got a couple of other programs here that you can try on your computer when you test it out later. So we now have a couple of binaries. Let's execute hello world. And it prints hello world. So we've injected a format string that contains a translated version of a brainfuck program and our interpreter and execute this as part of an execution to the format string. Let's execute the brainfuck code for the Sierpinski triangle. And we've printed the Sierpinski triangle. Hooray! So this is online. Go check it out on GitHub and play with it for fun. Let me conclude. So the low-level languages like C and C++ are here to stay. And they allow us hackers a huge amount of opportunities and allow us to play in very different and unintended ways. And we are working on the security side to defend against these opportunities. And on the hacker side, we're trying to explore new opportunities on both ends. So there's a lot of fun projects and fun research projects in there. The defenses that we design require a very careful policy and very careful design. And many of the current defenses, especially the ones that are deployed in our systems, are broken. And as we've shown, without stack integrity, they can easily be mitigated. So we need to get stack integrity out there and more people to use it. So if you're compiling with LLVM, use the safe stack. Make sure that an attacker cannot just use ROP on your program. And it comes with very low performance cost. And especially for the safe stack, it has negligible overheads. You will not even notice any difference to regular execution. And CFI, which is the hottest defense mechanism that is currently being discussed, makes attack harder, but is no panacea. So there are corner cases in there that still allows exploitation under CFI. So we need more principled defenses like memory and type safety that we are currently proposing and hoping to get into mainstream compilers so that all of you can profit from them and make your software more secure and resilient against any attacks. And with that, I would like to end my talk, and I'm happy to take any questions.
Okay. Before any question, we have one tradition in Serbia. It's your first time here?
Yeah.
I think so. You need to take one drink.
I like that. Are you going to join me
Others
too?
can join. Huh? Yeah. Somebody else? Yeah? There we go, guys. Yeah.
Živeli.
Surely.
That's cheers in Serbian.
Cheers.
Oh, yeah.
Surely.
Wait for me. Oh. Thank you.
Cheers. That was good. I like it here.
Now questions.
That was a huge shot. Any question, guys? Yeah. Do you guys have a microphone for?
With the type control stuff, you were talking at the beginning about controlling callbacks or call executions that are based on a particular type of object. Without packing, doesn't that increase a program's vulnerability to reverse engineering because the data descriptors are easier to trace?
Let
And I understand there's a trade-off.
me give you an academic answer. It depends. So the thing is, if you're reverse engineering, the majority of objects already has a vtable pointer, and you get the same information on that vtable pointer. So the information we use doesn't make a difference for the majority of programs. Now there's a slight amount of C objects that do not have a vtable pointer. For the subset of C objects or C classes that that do not have virtual calls and thereby a vtable pointer, we do add additional information to the program. But for example, in many large software projects like Chrome, the vast majority of classes already has virtual functions, and we don't add any additional information there. So it depends. It can add more information, but we strongly believe that the security benefit likely outweighs the additional increase in information that you give a potential reverse engineer.
Sure.
Thanks.
Hello. So I have a type safety question as well. What are the performance implications of that pass that you implemented?
The pass or at runtime?
Well,
Do you talk about the compilation time or the
No,
additional?
no, I'm talking about the runtime. No compilation time.
It's rather low, a couple of percent. But so we do have performance results in the paper, that is on my homepage. So you can just look at the paper itself and go and look through the details of the performance numbers. It's for the spec CPU programs, which are a common benchmark when evaluating performance overhead. It's in the single-digit %. And same for Google Chrome and Firefox. So it's a couple of %, but we are still working on optimizations. So this is a research prototype. I mean, we haven't pushed it to mainline LLVM yet. We are working on extensions to that system, and we'll hopefully push it sometime with even lower overhead. So we're still working on performance optimizations. So far, it's in the single-digit %.
Does community have any comments on the PASS? I mean, LLVM community.
So this paper will be presented in 4 weeks.
Oh.
So this was like a preview. So we haven't started upstreaming the patch yet.
Okay.
But we've released the source code, so you can check it out if you want to. We'll start upstreaming as soon as the code has settled. Remember, we are an academic research group, so we are developing a first prototype, then we're publishing it, then it takes some time until we actually go and upstream it.
Okay, thank you.
Thanks. There was one more. I think there's. Thanks.
Hi. I was wondering if on these attacks with the control flow that you shown with memcopy, what it would happen if you inline all of these functions? It would be better?
Sure. If you inline the code, you don't get a return instruction.
Yeah.
Without a return instruction, you cannot override the target. Luckily, these are libc functions, and most of the time they are not inlineable in the way they are developed. So we're still lucky there from the attacker's side. I do know that LLVM has primitives for some of these functions, and they try to inline their own versions of LLVM under some conditions. And as an interesting side note, we recently found a bug in some libc's version of memcopy that allowed other arbitrary behavior. But this might be a discussion point for the bar later on. Any other questions? Thanks again. Go play with the code.